संदीप भी नहीं है, मनीष भी होगा, मनीष तो तीनों को संगत को छोड़ूंगी।
हेलो
स्वामीनाथन सर, गुड मॉर्निंग।
अरे मैं तुमको छोड़ूंगी भाई, यहाँ तक छोड़ दूंगी, वो घर छोड़ेगा काम से। भाई अपने घर पहुंच के जो रिस्क लेना है।
हेलो स्वामीनाथन सर, गुड मॉर्निंग।
हेलो
ग्राउंड पर जाएंगे।
Hello, Swaminathan sir.
Hello.
Yes. Now you are audible.
Now it's audible, huh?
Yes, sir.
Yes, sir.
Okay.
Good morning, sir.
Hello. Good morning. How are you, madam? How are you?
Very good. I'm good, sir.
Okay.
How are you?
Fine. Actually, first I came to Nagpur long back. I think you remember
sir.
that?
Yeah.
Yeah, sure.
Remember that.
हेलो कुछ नहीं होगा।
दहा कंपोजन होत्या ना.
Hello, sir. Can we start at 11:45? Swaminathan, sir.
Yes, you can start now. No problem.
Hello. Hello, sir. Hello, Swaminathan, sir.
Hello?
Hello.
Ah.
Can we start at 11:45 now?
Yeah. You can start. I am ready. No problem. Like anytime.
Sir, you are audible, but now increase the volume.
No. Volume is the maximum. Actually, I put an external mic now.
Okay.
Is it okay now?
Yes, okay.
Okay, I'll keep the mic in the nearby.
Now it's okay. Now okay. Okay, sir.
Okay. Right.
Rashmi madam, we will start around exactly 11:45. Okay, na?
Okay, sir.
No. Audience are mainly with MSc students, na? MSc students. Huh? PhD and MSc. Right? Oh, okay. Right. Hello.
Hello, Rashmi madam. Okay.
Yes, sir.
Yes, you can start.
Start करने को Sir, can we start?
Yes.
Welcome and a very good morning to one and all present. I, Rashmi Dubey, welcome you all on behalf of Department of Chemistry, Kamla Nehru Mahavidyalaya, for today's guest lecture on fluorescence spectroscopy and its application. But before moving further, firstly, I pay my homage to late Sri Govindraoji Vanzari sir, founder president of Amar Seva Mandal, Nagpur. I also pay my gratitude to Honorable Dr. Suhasini Vanzari ma'am, Honorable Advocate Abhijit Vanzari sir, MLC Secretary Amar Seva Mandal, Honorable Dr. Smita Vanzari ma'am, Treasurer Amar Seva Mandal, for their constant support for organizing such type of events. Now, I welcome our today's guest, Professor M Swaminathan, visiting professor, IRC, Department of Kalaslingam Academy of Research and Education, Krishnapuri. I also welcome Dr. S.M. Gadegoni ma'am, Head of Chemistry Department, Kamla Nehru Mahavidyalaya, Nagpur. Dr. W.B. Gurnule sir, Department of Chemistry, Kamla Nehru Mahavidyalaya, Nagpur. And all the faculty members who joined this meeting and students who joined this meeting, I welcome all of you. But before moving further, I got an opportunity to introduce Dr. M Swaminathan. Sir has completed PhD from Indian Institute of Technology, Kanpur in 1983. He has 40 years of teaching experience at Annamalaya University as professor and chairman of organic chemistry. Presently, he is working as visiting professor, Nanomaterial Laboratory, International Research Center, Kalasalingam Academy of Research and Education, Krishnaguri. He guided more than 20 students for their PhD work and published more than 248 papers in national and international journals. He worked as Fellow of Royal Society of Chemistry and member of American Chemical Society. He is awarded with so many awards like Silver Medal Award, Bronze Medal Award, and Lifetime Achievement Award at RTMNU Nagpur. So today we have such a versatile personality with us, and I request Sir to present his slide and start the session. It's over to you, sir.
Okay. Thank you, Dr. Rashmi, madam, for the nice introduction. And I'll share the screen, please. See whether it has come.
Sir, your voice is not coming.
Okay.
Please increase your volume.
Is it okay now? I mean that. Hello.
Yes, sir.
So are you seeing the slide now?
Yes, sir. Your slides are visible, but not in full screen.
I'll just see that. So are you able to see it in full screen now?
Yes, sir.
Okay, thank you, madam. So it is a pleasure for me to deliver the lecture in Kamla Nehru Mahavidyalaya. Actually, today is a National Science Day, so both are coincidental. Maybe you know that it can take it as a lecture of National Science Day lecture anyway. And another thing is that Kamla Nehru Mahavidyalaya, I mean, is not new to me because I have visited this your college even long time back, maybe up 15 or 20 years back. I came for a conference.
Excuse
First
me,
time.
sir. Sorry.
Hello?
Sorry, sir. Excuse me. Sir, slides are not visible.
Is it? I mean, my slides are there in that. I mean, or hello.
Hello.
Now is it visible? I mean that.
Yes,
Hello.
sir. Yes, sir. Yes. Yes, sir.
Hello. Are you able to see now?
Yes, sir. Yes, sir. Slides are visible, but in window form.
In?
No, sir. Now it's not visible.
Actually, when I put that I mean full screen, it goes away. I mean that can I
Yes.
have it? I mean that.
Yes, sir. In full screen, it is not visible.
Now it's visible, now.
Yes, sir.
It is changing.
Yes, sir. It's changing.
Okay, when I make it a full screen, I think it goes away. So can I have it
Yeah.
like this now?
Okay.
Okay, you can enlarge it. I mean there itself. I mean that if you want. I mean.
Okay.
Okay, sir. Okay, sir.
Okay.
Yes, yes. Continue, sir.
Okay, right. So thank you very much. You know that as I told you in the beginning that Kamla Nehru Mahavidyalaya, this is not a first time. I have visited earlier also, and not only that. After that, the Nagpur city is an orange city, which is I frequently visited for so many conferences. So it's a nice place to see. Of course, that now there is no chances, so we are giving a webinar, and I am now working as a visiting professor, as they have told in the introduction, in a university called Kalasalingam Academy of Research and Education. and it is situated about 60 kilometers south of Madurai. All of you know about Madurai, and it is about 60 kilometers south of Madurai, and it is located at a place, exactly a very beautiful location. You can see that our university in the slide itself, and completely surrounded by the mountains of Western Ghat. Actually, these mountains are called Podigai Mountains. That is why one train is running from Chennai to this place is called Podigai Express. So this is an excellent place, and I joined here in the year of 2015. Still, I am continuing actually going to this place only because of this environment. So the environment is an excellent environment, and we can see that so much air purified, and all these people, whoever comes, a guest comes, that they will be more attracted by the environment. So thank you very much. Now we'll see today fluorescence spectroscopy and its applications. As far as my research is concerned, in IIT, I did my PhD only in the fluorescence spectroscopy. I mean, application of fluorimetric techniques for studying the excited state properties of the molecules, particularly the organic fluorophores, that is their acidity constants in the excited singlet state. So I started my research career only by using this fluorescence. Later on, I changed to so many fields, and presently we are working on the photocatalysis. Still, I'm very fascinated about this fluorescence spectroscopy. Now I started giving lectures on the fluorescence spectroscopy and the applications. Even I have written 2-3 articles in the ACT newsletter also. Professor Vasudev Gunale may be knowing this. So we have written that articles on the fluorescence spectroscopy also. So this is a very good subject and very, very highly sensitive analytical technique. Actually, whether you take it as UV or fluorescence, both are called analytical techniques. And we can only analyze or find out the concentration of the unknown substances by using the UV and fluorescence. And these are very sensitive because UV, you can go up to 10 power minus 5 molar. And whereas in the case of fluorescence, you can go up to 10 power minus even 7 molar. That is why this is called a very highly sensitive technique. So let us see the fluorescence spectroscopy and its applications today. All of us know that spectroscopy is a result of interaction of light with matter. So when that electromagnetic radiation interacts with the atoms and molecules and resulting in different types of spectroscopy like UV visible spectroscopy, infrared spectroscopy, NMR spectroscopy, depending on the frequency of light that we are using for getting the spectrum. So UV spectroscopy occurs only due to electronic excitation. So once it is absorbed, a photon is absorbed, then it can also emit. Both UV and fluorescence, they are called as electronic spectroscopy. So once the electron is excited to the ground state to the excited state in singlet state by light absorption or photon, and the electron at the higher energy state tends to lose energy by either thermal relaxation or by emission. So thermal relaxation, we don't get any emission, but if it loses the energy by emission, that emission may be fluorescence or phosphorescence, and that is generally called as luminescence. You might have heard the word about luminescence so many times. That's photoluminescence, thermoluminescence, chemiluminescence. It all depends upon how this electronic state is generated, excited state is generated. When the excited state is generated by a photon, and the luminescence, emission is called photoluminescence. Sometimes even by heating, you can go to the excited state and the emission may be there, that is called thermoluminescence. And in the chemical reactions, it can reach the excited singlet state and emit the light, that is called chemiluminescence. Most of us know about the fireflies, in which the chemiluminescence occurs, and that is only because of the chemical reactions. So there different type of luminescence is a common term which can be used for fluorescence or the phosphorescence. And both absorption fluorescence, they are called as I told you earlier, it is an electronic spectroscopy because it occurs due to the excitation of electrons. So in this lecture, what we are going to see is what are the basics of absorption spectroscopy, because unless the molecule absorbs, it cannot emit. So you cannot have a fluorescence if there is no absorption. So initially the absorption of light should be there. So basics of absorption spectroscopy is essential to understand the fluorescence parameters or fluorescent spectroscopy. Then we will see the fundamental concept of fluorescence, and then the instrumentation, and what are the different fluorescence parameters which are used for analysis, and what is the relation between fluorescence and the structure, and finally something about the applications of fluorescence. So as far as absorption is concerned, if you take an organic molecule, there are non-bonding electrons, pi electrons, and sigma electrons. If you take a benzene, we have only pi electrons. If you take an aldehyde, we have non-bonding electron as well as a pi electrons. So sigma electrons also will be there. So you know that you have sigma bond, pi bond, and also the electrons in the non-bonding orbitals. So the excitation by sigma to sigma star, or pi to pi star, or n to pi star result in the absorption of the light. And we have so many terms involved in that absorption spectroscopy. The Beer-Lambert's law is a basic law for absorption spectroscopy, that absorbance is equal to epsilon C into L. Absorbance, you know that we can measure by using the spectrophotometer, and epsilon is that molar extinction or molar absorption coefficient, C concentration, and L is the length of the cuvette or the path. And we have the bathochromic shift, red shift or blue shift, or increase in intensity like hyperchromic and hypochromic shifts. And you have a phenol, and the phenol, what will happen at pH of 5 or 6, it exists as a phenol. Whereas when you increase the pH, when you increase the pH, what will happen is phenol is converted into phenoxide ion. So when the pH increases from 5 or 6 to 11 or 12, then you have phenoxide ion at the pH of 11 or 12. So here you have phenol and phenoxide, both are in equilibrium. So when you have two species in equilibrium, then you can get this isobestic point. So isobestic point is an indication of the presence of two species which are in equilibrium. So what are the factors affecting the UV spectra? Or by using the UV spectra, what you can infer? Actually, when there is an increase of conjugation, then that will give a very good, redshifted UV spectrum. And the UV spectrum is also affected by the solvents, polarity of the solvents. See, if you take a benzene, it is a non-polar solvent, whereas when you take this water is a polar solvent. Hello?
क्योंकि स्पेक्ट्रोस्कोपी का ना ये आपके एमफार्म में भी काफी इम्पोर्टेंट है.
Hello?
क्योंकि आपको इसके लिए लगेगा एनालिसिस के लिए.
Some interference is there.
Are requested to please.
So when you increase that polarity of the solvent, the absorption spectra also changes, and the shift caused by the solvent polarity is called a solvatochromic shift. That is also one of the essential thing in the UV spectrum. And what are the applications of the UV spectra? I think even in the MSc labs, you have nowadays a UV spectrophotometer. You can measure the absorbance. Based on the absorbance, you can easily find the concentration by using a calibration graph. So it is used for the quantitative analysis. That is why it's called as analytical technique. And you can also find out the composition of the complex, whether the complex formed is 1:1 or 1:2 complexes. We can measure the acidity constant in the ground state, pKa value in the ground state, and you can also study the charge transfer complexes by using the UV spectrum. So now we'll see what is the fundamental concept for the fluorescence. This is a very famous diagram. All of you might be aware of this diagram. This is called the Jablonski diagram. This explains the origin of absorption as well as the fluorescence. You can see the blue line indicates absorption of light. That is, a molecule absorbs the light and immediately it is excited to the excited singlet state. Singlet state may be S1, S2, S3, S4 like that. So that is why we are given as S1, S2 and Sn. So there are so many singlet states depending upon the light that you are using for irradiation. The molecule goes to the singlet state. If the light is sufficient only for S1 state, it goes to S1 state. The light is more than that, it can go to S2 or S3 or S4 states. So what will happen is the molecule absorbs a photon and goes to the singlet state. After absorption of light, the molecule actually loses the energy. Actually, initially it loses energy by thermal relaxation. You can see in the singlet state, the vibrational states are very close to each other. So that what can actually that energy is lost in the vibrational levels, and the molecule comes to the V0 of the S1 level. So that is called the internal conversion. You can see a line that is pointing out the internal conversion. And so the molecule loses energy by thermal relaxation and comes to the V0 of the S1 level. And from the V0 of the S1 level, the band gap or the energy gap is very high. So now the molecule has no alternative except to emit, or it can also even lose energy by thermal relaxation if there are any intermediate levels. So here, if it loses the energy thermal relaxation, we don't get anything else. But if it loses the energy by emission, we get the fluorescence. So fluorescence comes from S1 state to S0 state. And from the S1 state, the molecule again, it can cross to the triplet state. So triplet state may be T2 or T3, T1 or T2 or T3. And finally, it comes to the T1 state, the V0 of the T1 state. And from the V0 of the T1 state, again, the molecule can lose energy by emission. If the emission is occurring from the triplet state, it is called phosphorescence. That is V0 of the triplet state. At the same time, the emission occurs from the singlet state, it is called fluorescence. So this is the difference between fluorescence and the phosphorescence. Both are emission of light. Only difference is the origin. The origin is V0 of the S1 state is fluorescence, and V0 of the T1 state is called phosphorescence. And here, when there are energy loss within the state, it is called internal conversion. If it crosses from singlet to the triplet state, it is called intersystem crossing. So what is the difference, basic difference between fluorescence and the phosphorescence? Both are emissions. So how to differentiate? Because we have to find that we have to differentiate the fluorescence and the phosphorescence. So here you can see, as we have seen in the Jablonski diagram, the fluorescence originates from S1, V0 of the S1 state to the S0, any vibrational state. And it is Stokes shifted to the absorption. What is a Stokes shift? Stokes shift is nothing but, that Stokes shift is generally here it is termed as red shifted to the absorption. Because that if the absorption takes place at 450 nanometer, certainly the fluorescence will take place only after 450 nanometers. Because it loses some energy in the by thermal relaxation, the vibrational state, it comes to the V0 of the S1 state, so loses the energy, then only it emits. So it is always, that 450 is absorption, means you will observe the fluorescence only at 500 nanometers or even 550 nanometers only. And another thing is it is independent of lambda excitation. Suppose if you use the excitation wavelength, the different excitation wavelength, you will observe only one emission. You will not observe different emissions, because as we have seen in the Jablonski diagram, you can see whatever may be the state it goes depending upon the light. Finally, it comes to the V0 of the S1 state, then only it starts emitting. So the fluorescence will not change depending upon the lambda of the excitation. And the lifetime, fluorescence lifetime ranges from nanosecond to the femtoseconds. That is 10 power minus 9 to 10 power minus 15 seconds. So this is a characteristic of fluorescence. What are the characteristics of phosphorescence? It actually occurs from the V0 of the triplet state to the S0 of the any vibrational state. And the T1 state is very close to S0 state. You can see the energy gap is very, very less, whereas the energy gap is more here. So that is why it is very close. T1 is very close to the S0 state. And the lifetime of the triplet state is longer lifetime. It is only in the microseconds, 10 power minus 2 to 10 power minus 4 seconds. Because triplet to singlet transition is a forbidden transition. That is why it spends more time. So these are the characteristics of the phosphorescence. So we should know what are the characteristics of fluorescence, what are the characteristics of phosphorescence. Then only we can easily differentiate both. So this is again that the characteristic of phosphorescence is given here. That is a time delay, because it has to go to the triplet state, then only emits. So there is a time delay, and it has a longer lifetime, larger redshift. For example, I told you in the beginning that if the absorption occurs at 450 nanometer, emission occurs at 500 or 550 nanometers. whereas the phosphorescence will occur only 600 or 650 nanometers. So because the energy gap is very less, so it goes to further redshifted. And the photochemical reactions are taking place in the triplet state. And because it has more time, it can spend more time, the lifetime is longer. So many of the photochemical reactions, they are taking place in the triplet state. And mainly all the carbonyl compounds, they are spending the time because they are n-pi star transition, they go to the triplet state. And that is why the reactions are taking place in the triplet state. And another thing is, generally phosphorescence is not observed at the room temperature because the energy gap is very less. Automatically it loses energy mostly by thermal relaxation at the normal temperature. Suppose if the temperature is very low, that is liquid hydrogen temperature, the molecule becomes rigid and it cannot vibrate. So you cannot lose energy by vibration. Then you can observe the phosphorescence. So generally to observe the phosphorescence, we have to go to the low temperature. I mean that like liquid nitrogen temperature only you can observe the phosphorescence. Otherwise at the normal temperature, you cannot observe the phosphorescence because most of the molecule, they lose energy by thermal relaxation. So nowadays, I mean, the research is advanced. Even room temperature, the phosphorescence can be observed. How we can observe the room temperature phosphorescence? We know that the molecule loses energy only by thermal relaxation or vibration relaxation. So if you restrict the vibration either by low temperature or by using some other molecules like micelles or cyclotrexins, you know, micelles, they will be binding the molecule. So the vibration is restricted in presence of micelles. Or if you take the cyclotrexins are bucket type of molecules. So the molecule actually goes and fit into the bucket so that its vibration is restricted. So nowadays they are observing the phosphorescence at room temperature in presence of micelles or cyclotrexins. So that is called room temperature phosphorescence. And there is one rule called Kasha's rule. It's a hypothetical rule. And here, what is that rule is?
Moderation ही करा आणि conductor ही रहा.
Hello? So if the electronic transition is pi star, the molecule will be highly fluorescent. So it's a general, rule, but it's not a hard and fast rule. But generally, if the molecular transition, electronic transition, the lowest electronic excited state, singlet state is pi star, then the molecule will be highly fluorescent. Sometimes the lowest excited singlet state may be due to n pi star transition. In that case, it will be weakly fluorescent or highly phosphorescent. So if you take this benzene or naphthalene or anthracene, whatever it may be, naphthalene, anthracene or perilene or phenanthrene, then mostly we have only pi electrons. So the transition will be only pi star. The lowest state will be pi star transition. So it will be, they are highly fluorescent. Whereas when you take, diphenyl ketone or any other ketones, there are non-bonding electrons. The lowest electronic excited state will be n pi star state. So these compounds are highly phosphorescent and very weakly fluorescent, according to the Kasha's rule. So that's all about jumping about what is the origin of fluorescence spectroscopy and phosphorescence spectroscopy. Now we'll see basic instrumentation for a fluorimeter, spectrophotometer. Actually, there are different type of fluorimeter. Basic fluorimeter is a steady state fluorimeter. And another one is time resolved, but time resolved is not necessary now, but general for applications, it's enough if you have that, steady state fluorimeter. So that, it looks slightly complex, but this is a block diagram. Actually, this is a diagram which is we have used for the fabrication of a spectrophotometer in IIT Kanpur. During my PhD, one chapter is only fabrication of a spectrophotometer. We fabricated a fluorimeter, and that fluorimeter was working for about more than 10 years and paved the way for the more than 5 to 6 PhD students. So this is actually, you can see a lamp. This is a lamp, maybe a mercury lamp or xenon mercury lamp. It gives light radiation in all the wavelengths. And this is a monochromator. It's called excitation monochromator. And this is a sample compartment where you can place your cuvette, and then that maybe quartz cuvette, and the sample solution also. And this is another monochromator. This is called emission monochromator, and this is a detector. So basically, a fluorimeter requires these 5 components. That is lamp, monochromator, sample compartment, another monochromator, and a detector. And this is a basic requirement for a steady state fluorimeter. So what will happen is the lamp is giving the different wavelength of light, and this excitation monochromator selects a wavelength for excitation and focus on this sample, which is placed in the cuvette of the sample compartment. And here the fluorescence occurs at all directions. And whereas to avoid the scattering, normally fluorescence is measured only at 90 degrees centigrade. So at 90 degrees, the scattering will be very less. So at 90 degrees, we have the emission monochromator. The emission monochromator actually finding out the intensity of emission at different wavelengths, and that is detected and it goes to the recorder. And this is actually because the lamp as well as monochromator, they are not equally efficient at all the wavelengths. So generally, to find out that corrected excitation spectra and emission spectra, they have this circuit diagram, and this is not essential. Earlier we used to take that values and then find out that excited state, corrected excited spectrum and corrected emission spectrum. But nowadays the instrument itself is sophisticated and corrects everything in the instrumentation itself. So we can get whatever the spectra that we are getting is the corrected excitation spectra and corrected emission spectra. So this is the one which is used for measuring the fluorescence spectrum. And sometimes we may require the fluorescence spectrum at the low temperature, that is at the liquid nitrogen temperature. So here the same sample compartment is different. It has 2 holes here, and this is a circular one. And here this is a gel doll flask with which you are filling it liquid nitrogen, and this is a sample tube just like an NMR tube. And here you are having the sample. When you put it in the liquid nitrogen, it gets frozen, and this is directly inserted here. Then immediately it is irradiated. You can find the fluorescence at the low temperature. But the same setup is used for measuring the phosphorescence also. But phosphorescence, you have to use a chopper motor, because we know that how to differentiate fluorescence and the phosphorescence basically by a time delay, because there is a delay in time of the emission in the case of phosphorescence. That delay is made by the chopper motor. It is having a 1 hole. One time it opens for the radiation, and after rotation, full rotation, it opens for the emission, so that you can see the delayed emission by using this chopper motor. So this is a setup for finding out the low temperature fluorescence as well as for the phosphorescence. So that's all about this, diagram for this, block diagram for the fluorimeter and the phosphorimeter. There's no phosphorimeters, only fluorimeter is used for measuring the phosphorescence also. And another thing is, now we'll see what are the different parameters available for in the case of fluorescence. See, the advantage of fluorescence is fluorescence has a number of parameters. In the case of UV, you have only 1 parameter. What is that? 1 or 2 parameters, that is absorption spectra. Changes in the absorption spectra, you can find it out, or absorbance. Whereas in the case of fluorescence, they identified more than 14 different parameters, and they have been used for clinical, biological, and environmental and sensor applications. You can see that most of the biological labs, they have the fluorimeter. Initially, whenever we started our work, in Annamalai University also, wherever that, only the biology lab will be having a fluorimeter, because the biological samples or the biological molecules, they are fluorescent. Their concentration can be easily measured by using the fluorimeter, because even at the trace level, we can measure the concentration by using the fluorimeter. So now we cannot go into the 14 different parameters. We'll see some of the common fluorescence parameters, which are used for the general applications. So what are the common parameters? One is a fluorescence emission spectra, just like absorption spectra, fluorescence emission spectra. Then you can measure the intensity, shape, and peak position, and Stokes shift. So Stokes shift is nothing but difference between absorption maxima and emission maxima. That is called Stokes shift. And another parameter is fluorescence excitation spectra. In the case of emission spectra, lambda excitation is fixed. and you are scanning this emission monochromator and getting the emission spectra. Whereas in the case of excitation spectra, emission is fixed. So you know that emission occurs 550 nanometers, emission maxima they fix it and then vary that lambda excitations. That is that excitation monochromator is scanned. So that spectra obtained is called fluorescence excitation spectra. And one more is called synchronous fluorescence spectra. We are going to see that is a simultaneous scanning of excitation and emission monochromators. And another parameter is called fluorescence quantum yield, which is very, very important parameter that shows whether the molecule is highly fluorescent or weakly fluorescent. And that is a measure of the fluorescence intensity that is called fluorescence quantum yield. And fluorescence lifetime. So how much is that? What is the lifetime of the molecule when it loses energy only by using the fluorescence? That is called fluorescence lifetime. So these are the different parameters which are commonly used. So we'll see one by one. What is the fluorescence emission spectra? As I told in the beginning, that intensity of fluorescence depends upon the intensity of excitation wavelength. The I is called intensity of excitation wavelength, and the A is the absorbance at lambda excitation. Suppose you are using 250 nanometer for excitation. What is its absorbance at 250 nanometer for the molecule? That you have to substitute here, absorbance, because depending on the absorbance, intensity of fluorescence also may vary. And finally, another one is called quantum yield. When the molecule is highly fluorescent, you will have more intensity. When the molecule is weakly fluorescent, you will have the less intensity. So the intensity of fluorescence depends upon three factors: intensity of excitation wavelength, absorbance, and quantum yield. So that is why in the case of UV, you can use the absorbance for in the equation. Whereas in the case of fluorescence, it is only an arbitrary unit. You can see all the fluorescence spectra. In the fluorescence spectra, they can see, and that they will give only IF as an arbitrary unit. There is only the numbers are there. Whereas in the case of fluorescence, you can see 0 to 2, that absorbance. So generally, to measure the concentration of any molecule by using fluorescence, a calibration graph is a must, because intensity of fluorescence not only depends upon these factors, it also depends on the instrument, characteristic of the instrument. That is why sometimes when they report some spectra, they'll also report the type of instrument they are using it for this one. And the Stokes shift, as I told in the beginning, this is also another parameter: lambda max absorption and by lambda max emission. And another thing is fluorescence emission spectra. As I told in the beginning, the emission is fixed, excitation is scanned. That is called fluorescence excitation spectra. And quantum yield. What is the quantum yield? Fluorescence quantum yield is actually very difficult to measure the absolute quantum yield. Absolute quantum yield, you have to measure the intensity of fluorescence at all lambda at all directions and divide by the light absorbed. So here it is very difficult to measure the absolute quantum yield for all the molecules. So what they have done is they have taken some representative fluorophores, that is highly fluorescent molecule, and they measured the absolute quantum yield, and using that the relative quantum yield is measured and reported for all the molecules. So if you take the quinine sulfate or anthracene, they have taken anthracene or quinine sulfate, for which the quantum yield, absolute quantum yield, is known as 0.55. And so based on this, we can measure the relative quantum yield for all the molecule very easily. So suppose if you take that one is at quinine sulfate, so F1 is equal to I1, A1 and Psi1. Actually Psi1 is known and A1 is absorbance at the particular wavelength of excitation for this quinine sulfate, and I1 is the intensity of light at the excitation wavelength. All these are known. Whereas in the case of F2, I2 you can measure intensity, you can measure that, F2 you can measure because that is the area of fluorescence, and I2 is the intensity of the excitation wavelength that also you can measure, and absorbance also you can measure. Psi2 is unknown. So you can see Psi2 is equal to F2 A1 Psi1 by F1 A2, and this is called relative quantum yield. Normally they report only the relative quantum yield for all the molecules, not the absolute quantum yield. Hello. And lifetime measurement. Actually, lifetime measurement is used by an instrument called time correlated single photon counting. That is, they excite with a laser pulse and then they measure the decay. How much the molecule, the fluorescence decays by measuring their photons. And by using the decay curve, they can easily find out the lifetime of the molecule in the excited singlet state. And this is the equation. When the fluorescence intensity comes to 1 by E of its level, that time is called a lifetime. So here you can see that it is excited by a laser pulse. The intensity decreases. The decrease in intensity when it comes to 1 by E of its level, the time required is called a lifetime of the molecule. So this is a lifetime of the excited singlet state. And from this, you can measure the lifetime of the fluorescence. How to measure the lifetime of the fluorescence? So tau 0 is known by the experiment. That is lifetime, tau 0 is known by the experiment by using this single photon counting method. That is, this is nothing but a lifetime of the excited singlet state. And what is the fluorescence lifetime? That is equal to tau 0 into psi f. That is quantum yield. When the molecule loses energy only by the fluorescence, psi f is equal to 1. Quantum yield is 1. So in that case, tau f is equal to tau 0. Whereas in the quantum yield is 0.55, then tau f is equal to tau 0 into 0.55. So from this, you can measure the lifetime of the fluorescence. Fluorescence lifetime can be measured very easily. And this is a method to find out the lifetime. So that's all about these, parameters, different parameters. We'll see some 2 or 3 spectroscopy, different spectroscopy, just a glance, not in deep. What is a synchronous fluorescence spectroscopy? What we have seen is, steady state fluorescence spectroscopy, in which we have seen that, this emission spectra, excitation spectra, and other parameters. And what is a synchronous fluorescence spectroscopy? Here you can see the figure it can explain very easily. This is conventional fluorimetry. That is, excitation spectra is, emission is fixed, and excitation monochromator is scanned. This M is a monochromator that is scanned. So you get the excitation spectra. In the case of emission spectra, excitation is fixed, lambda excitation is fixed, and you are getting that scanning the emission spectra. Emission monochromator. So you are getting the emission spectra. This is conventional. Whereas what is a synchronous fluorescence spectroscopy or fluorimetry is simultaneously scanning both excitation as well as emission. So this is a synchronous fluorescence spectra. That is, suppose if the lambda excitation is 250 nanometer, they fix the lambda emission as 270 nanometers, and both are scanned simultaneously. When this is 250, that is 270. This is 255, that is 275. This is 260 means that is 280. So the delta lambda is completely maintained. So by maintaining the delta lambda, they get a spectrum, and that spectrum is called a synchronous fluorescence spectra. That is very useful because instead of having so many maximas, this spectrum concentrates at one maxima and increases its intensity. By using that intensity, you can measure. Actually, this is mainly used to measure the concentration of a particular component in a mixture, just like kerosene petrol mixture. So mainly this synchronous fluorescence spectra is used in the environmental applications. So you can see this perilene. Perilene is nothing but 4 benzene rings are fused together. This is an excitation spectra and this is an emission spectra. At the same time, if you have the delta lambda is 30 nanometer, this is a synchronous spectra. You can see only you are getting one peak which is having highly intense. So in that case, you can make use of this and find out the concentration of the particular perilene in the mixture. Actually, Dr. A.K. Mishra was doing so many experiments by using the synchronous fluorescence spectra in his laboratory, and they were using, actually they identified the percentage of petrol in the kerosene petrol mixture. Of course, nowadays the kerosene is not easily available because it's not there. People, they forget about kerosene. But earlier the kerosene was supplied only through cooperative stores or ration shops. So the kerosene was very cheap. At the same time, petrol was costly. What they do is in the bunks and other places, they mix the kerosene with the petrol. So this contamination can be easily found out. So this is a spectrum of petrol and this is a spectrum of kerosene. At a different concentration, you are getting the synchronous fluorescence spectra like this. And based on that, you can find out what is the percentage of petrol in the kerosene petrol mixture. This is possible only by using this synchronous fluorescence spectra. And this is again, in Gulf countries, we have so many, that oil wells and other things. And there is one, spectrum called EEM, and that is emission, excitation, emission matrix. So here, this is also called a three-dimensional fluorescence spectroscopy. This is an intensity, this is an emission wavelength, this is the excitation wavelength. And when you, with the different excitation wavelength, when you measure the intensity, you get a graph like this 3D spectrum, and this is a contour map. And this is actually a 3D spectrum. And from this, you can find out a characteristic of an oil. That is, this is a characteristic of an oil. This is actually a characteristic of the Arabian crude oil. Similarly, this characteristic, you can find it out. And based on that, you can see this is the oil obtained from this place or from the other places like that. So these are the different ones. And one more spectrum is called a time-resolved fluorescence. Steady state fluorescence we have seen. So, we have seen that fluorescence spectra, excitation, emission, of that's called a steady state fluorescence. Time-resolved fluorescence is, as soon as it is excited by the laser pulse, immediately within a nanosecond, we are finding out the fluorescence. And nowadays, because of the sophisticated instrumentation, it is possible to measure the fluorescence immediately after excitation. That is, they excite with the laser pulse, and then immediately they are finding out the fluorescence like this. So you can see this is a fluorescence, immediate fluorescence. Then after 1 or 2 nanoseconds, this is after attaining the Frank quantum excited state. That is a relaxed fluorescence. So you can see 1 nanosecond, 2 nanosecond, and 3 nanosecond, you can find the fluorescence. So this is very useful to find out that changes that is taking place at a very fast in the excited singlet state. That is why this is called a time-resolved emission spectra, which normally we are not using it. Only in some sophisticated cases we are using this spectrum. See, that's all about these, different type of spectroscopic techniques. And we will see what is the, relation between fluorescence and the structure. Because people think that any molecule can be, measured by fluorescence. No, it's not possible, because all the molecule that is absorbing will not be fluorescent. Because most of the molecule, they absorb the photon. But some of the molecules are fluorescent, some are not fluorescent. So how to find out whether a molecule is fluorescent or not? So it is not, and there is no hard and fast rule, but there are some generalization by which you can have an idea that a molecule will be fluorescent or not. So what are the some generalizations? A molecule with a pi electron system of increased conjugation may be fluorescent, mostly. And a system with less number of substituents. If you have more number of substituents, then it will not be fluorescent. With the less number of substituent will be fluorescent. And the lowest S1 state is pi star. That is a Kasha's rule. And orthopara directing groups, they increase the fluorescence efficiency. Molecular rigidity increases the fluorescence emission. Heavy atom substitution reduces the fluorescence efficiency. Actually, for each one, we can find an example for this. You can see vitamin A is fluorescent. At the same time, if you have the cyclohexene or with cyclohexene 1 conjugated double bond, that's not fluorescent. Whereas the vitamin A1 with an increased conjugation, it is found to be fluorescent. Similarly, benzene, naphthalene, all of increased conjugation, the fluorescence intensity increases when you go from benzene to naphthalene. And fluorescent, benzene is fluorescent, whereas trimethyl benzene, 1,3,5 trimethyl benzene is non-fluorescent. Why? Because it has more number of substituents. So when you have more number of substituents, the vibration is there. So mostly the molecule loses energy by vibration relaxation or thermal relaxation, not by emission. So that is why the system with the more number of substituents are less fluorescent or non-fluorescent. And this is actually they compare with an engine. Suppose if you take an engine, and in the engine with the loose bolts will have the lowest efficiency. So like that, like loose bolts reduces its, efficiency is reduced. Here, if you have more number of these substituents, the fluorescence intensity also decreases. And this naphthalene S1 state is pi star, whereas in the case of quinoline, it is S1 state, lowest state is n pi star. So this is non-fluorescent and this is fluorescent. And similarly, if you take an aldehyde, It is non-fluorescent because N-pi star transition, whereas that aniline or phenol is here this lowest transition is pi star, so this is fluorescent. And the molecular rigidity, this is very, very important. You know that phenolphthalein, this is a structure of phenolphthalein. Phenolphthalein is non-fluorescent, whereas in which the carbon is bonded to 3 phenyl rings, which are easily vibrationally, they can lose energy. But at the same time, if you fuse 2 rings by an oxygen bridge here, so this becomes highly fluorescent. So fluorescein is also used as a fluorescent probe. So this is a very highly fluorescent molecule, fluorescein. This is only because of the molecular rigidity here. The same thing, that is, the vibration is restricted, so it becomes a conjugation is increased, the molecule becomes planar, so that is why it is highly fluorescent. Similarly, another example, malachite green is non-fluorescent, whereas when the same thing it is fused by the oxygen bridge, rhodamine B is highly fluorescent. And a heavy atom also, like fluorine, chlorine, bromine, iodine. Iodine is a heavy atom. So when you have the fluoronaphthalene, fluorescence intensity high, phosphorescence is low, so the ratio is 0.068. Whereas when you take the ironaphthalene, phosphorescence is very high, whereas fluorescence is very low, so the ratio is more than 1000. So generally, the heavy atom induces a S1 to T1 transition. So T1 transition is induced means it can only be phosphorescent, not fluorescent. So that's all about these fluorescence and the structures. Now let us see some of these applications. So the applications are, a few applications we can see. That is a highly sensitive analytical technique. 10 power minus 6 is normal. Sometimes it can go up to 10 power minus 7 molar. If the molecule is highly fluorescent, it can go up to 10 power minus 7 polar. So as I told in the beginning that UV you have only one equation, whereas you have so many parameters in the fluorescence, you can check the purity of the molecule by using this fluorescence. How to check the purity of the molecule? Suppose if you have a single molecule, like that only naphthalene is there, if you use different excitation wavelength, you will get only one emission spectra. So when you get only one emission spectra with a different excitation wavelength, that means that shows the molecule is highly pure. Whereas sometimes if the molecule contains benzene and naphthalene, depending upon the excitation wavelength, you can have two different or a mixed spectrum, or the spectrum changes, emission spectrum changes. So this is used for purity of the molecule, and the concentration can be determined by using the calibration graph. See, intensity of fluorescence for different instrument. That is why we have to use the calibration graph every time. And you can analyze the mixes by using the different excitation wavelength. And finally, this is very, very important. We can find a change in physical properties of the molecule in the excited singlet state. What are the physical properties? Acidity constant, dipole moment, geometry, like that. All these physical properties can be analyzed. See, when you take the UV spectrum, where from the UV spectrum originates, it originates from the S0 state and goes to the S1 state by absorbing a photon. So that is why UV spectrum can reveal the characteristics only in the ground state, because it starts from the ground state. Whereas in the case of fluorescence, it starts from the excited singlet state. So the molecule starts its emission from the excited singlet state. So whenever you want to study the property of the molecule in the excited singlet state, the only technique that you can use is only fluorescence. Only by using the fluorescence, you can find the acidity constants in the excited state, dipole moment in the excited state, or geometry changes. All these changes that occur in the excited state can be revealed only by using this fluorescence. So we actually, as I told in the beginning, that our PhD, my PhD is mainly that acidity, measure of the excited state acidity constant in the excited singlet state by using the fluorimetric techniques. So here, you know that 3 amino acids, tyrosine, tryptophan, and phenylalanine. So you can see that absorbance is overlapping too much. Whereas when you take the fluorescence, the overlap is very less. So by using the fluorescence, you can measure the concentration of tryptophan in the mixture. You can choose this wavelength, or you can choose this wavelength to measure the concentration of phenylalanine. Whereas in the case of tyrosine, there are overlapping is there. For that, you can use a different excitation wavelength where the phenylalanine will not absorb. Suppose if you take this excitation wavelength, the phenylalanine will not absorb because it has no absorbance here. So by using the different excitation wavelength, you can measure the concentration of tyrosine. So by which the fluorescence can be used to find out the concentration of a particular molecule in the mixture. And the change in acidity and basicity constants. That is also very useful thing. If you take that naphthol, alpha naphthol, beta naphthol, all of you know about alpha naphthol and beta naphthol. Earlier we know that the pKa value of alpha naphthol is around 9. pKa value is around 9. Only at the pH 9, what will happen is below 9 it exists as naphthol, and above 9, that is 10 or 11, it exists as naphthoxide ion. So the equilibrium, that is acidity constant, is only around 9, and there only it changes from OH to O minus ion. Whereas in the excited state, they found out alpha naphthol or beta naphthol in 1950. Weller reported this one. First time he reported. Even at the acidity, that is even at the pH of 1, it loses at H plus, forming O minus ion. So it becomes highly acidic in the excited state. So naphthol can become more acidic. Similarly, SH can become more acidic. NH2, they become more acidic. So they become stronger acids. Whereas in the case of COOH and CORR, they become more basic. That is, basicity increases in the case of carbonyl compounds, and acidity increases in the case of phenol and aniline and other thiol and other molecules. So they reported the increase in acidity or increase in, that is a decrease of pKa. pKa star is 9.8 for alpha naphthol, whereas you can see the excited pKa is -1. -1 in the sense below pH 0. That is why it is called a -1. So you can easily find out this excited pKa by using this fluorimetric technique. One is called a theoretical technique, that is pK minus pK star is equal to 2.1 in 10 power minus 3. And this is a Stokes shift. Absorption maxima at that naphthol, absorption maxima, of this naphthoxide ion. So this is in terms of the wave numbers, you have to put it here. Another method is fluorimetric titration method, in which if you take that intensity of fluorescence with and without, that I by I0 against the H0 or pH value, and if you take that phenol decreases, phenoxide ion increases, there is a crossing. At the crossing at what is a pH or H0, that is called a pKa value, excited state pKa value. This is a fluorimetric titration method. So by using this fluorimetric titration, we can find out the excited state pKa value. Another one is they are able to find out phototautomerism. What is a tautomerism? Tautomerism, all of you know that a proton from one place, it is going to the other place. In the case of COOH, you can see, and OH, salicylic acid, the tautomerism is actually the OH hydrogen goes to the oxygen, so that it forms a zwitter ion. So this is called a tautomerism. You know that we have seen that keto-enol tautomerism, very famous one, and you might have studied, you are familiar with the keto-enol tautomerism. Likewise, you can see here, this is actually keto-enol, this tautomerism. Like this, you can, here OH, the proton is, because this becomes more acidic, OH becomes more acidic, and the CO becomes more basic. What happened in the excited state, automatically the proton from that OH gets detached and then attached with the carbonyl oxygen, forming a zwitter ion. This they found out only by measuring the fluorescence. So what they have found is the salicylic acid, they have the fluorescence of 440 nanometer, where the orthoanisic acid is having the fluorescence of 340 nanometer. So the large difference is only due to that emission for salicylic acid occurs from the zwitter ion, whereas in the case of emission from the orthoanisic acid occurs from this same ion. There is no tautomerism here. So that is the reason this is called a intramolecular phototautomerism. Similarly, there are so many molecules, by using this, they found out this tautomerism, intramolecular phototautomerism, the synchronic acid and 4-methylampaliferone. And actually, this is our research work, and we studied 5-amino indazole. And the 5-amino indazole, excitingly, we found out instead of a blue shift, we observed a red shift. So immediately we analyzed, we found out there are two equilibria. The ground state equilibrium is different from the excited state equilibrium. The ground state, you can see that amino group is protonated, whereas in the excited state, you can see that pyridinic nitrogen atom is protonated. Same monocation, but both are monocations. This is a monocation formed with the protonation of amino group. This is a monocation formed with the protonation of the pyridinic nitrogen atom. So likewise, we are able to find it out. And at that time, it was, this phototautomerism were very famous. And immediately, as soon as we observed this and we analyzed this by using the low temperature, by another, so many other techniques. And when we reported this, the JAX, immediately it was accepted without any modifications. And now it has come in the book also. There is a one proton application, the chemistry, and they have given a very description about this phototautomerism that we reported at that time. So another very, very interesting aspect of this fluorimetry is, suppose the molecule changes its shape in the excited state, that we can easily find it out. So if you take anthracene, you can see the anthracene is a planar molecule. Even at the excited state, there is no change in the planarity of the molecule, or there is no change in the shape of the molecule. So that is why you are getting, this is an excitation spectrum and this is an emission spectrum. Both are having the mirror image. So when you have the mirror image of the excitation spectrum and emission spectrum, that means the molecule does not undergo any change in the excited singlet state. Whereas when you take a biphenyl, you can see this is an absorption, a broad spectrum, whereas emission is entirely different, a structured spectrum. That shows the molecule undergoes some change in the shape. That is a biphenyl molecule. You can imagine a biphenyl molecule. Biphenyl molecule, that is one plane, one phenyl ring is at one plane, another phenyl ring is at the other plane. So it is a twisted in the ground state. Whereas when you excite the molecule, it becomes planar. Because the conjugation increases, so it becomes planar. So because of the planarity attained, it has a structured spectrum in the fluorescence. So you can easily find out when there is no mirror image, that means the molecule undergoes some change in the shape. So similarly, we found out taken the 4,4-diamino biphenyl, and we found out the fluorescence is exactly matching with the 2,7-diamino fluorine. Though there is no CH2 group here, it becomes planar and it emits like 2,7-diamino fluorine. So this is one of these application by which you can find out the change in the shape of the molecule in the excited singlet state. Similarly, if it forms a dimer, you can easily find it out. Excimer is excited state dimer. So you can see that is here when the concentration is very less, you are getting a structured spectrum. When the concentration increases, this spectrum increases. So this is due to the formation of a dimer. So you can study the excited state dimer or excited state complex, that is a exciplex. So both can be studied by using this spectrophotometer very easily. So another thing is, whenever a molecule is excited, what will happen is its dipole moment changes. So because electron is going from one place to the other place, automatically its dipole moment will change. So you can find out the excited state dipole moment very easily by using this Stokes shift. Stokes shift, I told you in the beginning, what is a Stokes shift? That is a difference between absorption maxima and fluorescence maxima. Here you have to use the absorption maxima in the wave number scale, because that is a linear scale. Wavelength scale is not a linear scale. So you have to use it in the wave number scale and find it out. So you have to find it in the wave number scale, and in the wave number scale, you can find it out delta nu, that is Stokes shift, that is equivalent to delta nu squared, that is a difference between the ground state dipole moment and excited state dipole moment. Or 1 minute. 450. So excited state dipole moment, and the delta nu, you can easily find it out. So mu minus nu star is equal to, this is the equation. This equation is called a Lippert equation. So by using the equation, they found out this difference between the two dipole moments, nu star and nu. You can see that the change in dipole moment is equal to 9 dB units for this 2-amino naphthalene 6-sulfonate. Whereas this compound, you can see that the difference is 19, 20, even 40, 44 also. So the dipole moment changes very, very high. You can easily find out the dipole moment changes. A lot of research is going on to find out the dipole moment in the excited singlet state. And this is actually solvatochromic shift. That is when you go from a non-polar solvent to the polar solvent, and that maxima changes. That is called solvent shift. So you can see here, this is a spectrum of 2-anilino-naphthalene cyclohexane, and this is a spectrum in water. See how much maxima changes occurring here. This is around 370, whereas this occurs around 475. So nearly 100 nanometer change is possible by using this, changing the solvent. And this shift, solvent shift, is very, very useful to find out the polarity of the environment in the biological molecules. You take a fluorescent probe, and the fluorescent probe, you put it in the biological specimen and find out the maximum. Based on that polarity, you can, based on that maxima, you can find the polarity of that environment. So this is another molecule, anilino-naphthalene sulfonate. You can see this is now 1, and A is azonitrile, and D is water. So you can see the changes. So this is that Stokes shift. By using the Stokes shift, you can find the change in the, this is another equation. The delta F is given here. Delta F depends upon the dielectric constant and refractive index. So another one is finally, you can see the quenching experiments. Quenching experiment is nothing but if they take a fluorescent of the molecule, we add something else, the fluorescence intensity decreases. That is called quenching. Sometimes the fluorescence intensity increases. That is called enhancement. So here you can see the intensity of fluorescence without the quencher and intensity of fluorescence with the quencher, and that is given by the equation called 1 plus K SV into concentration of the quencher. This is called Stern-Warmer equation, and this called constant is called Stern-Warmer constant. So this is actually very, very useful to find out that interaction between the fluorophore and the quencher. Actually, when the curve, if you plot I0 by F by IF versus concentration of the quencher, then you get Stern-Warmer plot. The plot is linear, then you get one. Actually, there are two types of quenching mechanisms. One is called static quenching, another one is called dynamic quenching. And if the quenching is only having one mechanism, then you will have the linear plot. So this is a static quenching and dynamic quenching. When the quenching plot is non-linear, that means there is a mixed quenching. Both static and dynamic quenching are operative. That you can differentiate by using the lifetime of that molecule. So this is by using the lifetime of the molecule. So static quenching, actually when there is a static quenching, absorption spectra also changes with in the presence of the quencher. So static quenching means tau 0 by tau will not change. Only I0 by IF will change. And nowadays, you might have studied, you might have seen the papers like on-off switches. That is, what is an on-off switches? Actually, when you give many organic molecules nowadays, they synthesize, and they are using these synthesized organic molecules as fluorescence sensors because they are highly fluorescent. When you put a metal ion, the fluorescence may increase or may decrease. Here you can see a molecule. This is a molecule. So in this molecule, actually, this is a non-fluorescent molecule. And what will happen is, actually, this is a electron transfer makes the compound. Actually, this is a highly fluorescent. Yes. This is a non-fluorescent molecule. When you take a metal ion, it binds. So again, it becomes planar and indication conjugation increases. So its emission increases. You can see this is the emission of plain molecule. And when you increase the concentration of the metal ion, its emission increases. So there is a fluorescence enhancement of this molecule, bisoxo molecule. And that is why it is called off-on switches. This is called off-on switch for a zinc ion. So zinc ion can be sensed by using this one. Similarly, if you treat this molecule, actually the fluorescence this is highly fluorescent molecule. When you put a metal ion, the fluorescence gets quenched. So here you can see this is the fluorescence of the molecule. When you put the metal ion, the fluorescence getting quenched. So this is called on-off switches, because this is already highly fluorescent, then becomes non-fluorescent. So this is called on-off switches. So many papers like quenching mechanism making us off-on switches or on-off switches. So what we have seen is an intrinsic fluorophores. That is basically they are fluorescent, and sometimes some system may not be fluorescent, but how to study the system by using the fluorescent molecule? We use some highly fluorescent molecule, add the highly fluorescent molecule to the system, and they are called as extrinsic fluorophores. So these are rhodamine B. They are highly fluorescent molecules. You can add this fluorescent molecule to the system which is non-fluorescent, and the fluorescence of this molecule changes. Based on the changes, you can observe something else, and you can get more information about this one. So you can see this. This is again a fluorescent probe, and cadmium selenide is also, this quantum dot is highly fluorescent, and you can see by using the copper ion, it gets quenched, and you can sense the copper ion by using the cadmium selenide quantum dots. So that's all about this fluorescence quenching and application. And nowadays the drug complexation with CD cyclotexins are being used, because when you take a drug and complex cyclotexin, it is found to be more useful. Actually, there are so many advantages of the drugs with the complex with the molecule. What is the use of fluorescence? Fluorescence can study what is the complex formed, what is the complexity constant, all these things can be studied. Similarly, nowadays they use this fluorescence in the medicine department, and the majority of the cancers are being diagnosed by a large scale making this fluorescence spectroscopy, because this spectroscopy is a more sensitive and rapid diagnostic tool, and they are using this technique to find out that cancer cells, and it is used as a diagnostic tool in that medical field also. So these are some of the applications. By this I am completing this one applications. So we have seen what is a fluorescence spectroscopy, what is its principle, what are the different relation between structure and the fluorescence, and now we have seen some of the applications. And there is one reference called J.R. Lakovis. Actually, this is the like Bible for fluorescence, and so many editions have come. Even 2006 there are 2 editions. Those who are practicing research or even to study, and there are 2 volumes. Everything is available in this book, and it's called Principle of Fluorescence Spectroscopy, J.R. Lakovis. And other than this, there is an fluorescence, the Journal of Fluorescence. Every 2 years they are, giving a review on that development in the fluorescence. So by using that, you can get more information about the fluorescence. And this is another reference for the 3D fluorescence spectroscopy.
Hello, Adibaji.
So thank you very much, for your sharing. And this is our Lord Nataraja temple at Chidambaram. Thank you very much. This is a golden roof. So this is why it's a golden roof. It contains a golden roof. Thank you very much. So thank you for hearing, and it's my pleasure to answer any questions on the fluorescence spectroscopy. Thank you very much.
Thank you, sir. Thank you very much for this informative session. The information given by you is very, very helpful for all of us. Thank you so much, sir. From participant sides, if you have any questions or queries to ask, you may ask to sir.
So I can let them put it in the chat box also if it is not, clear to me.
Yes.
Okay?
Yes, sir. Or you put your question in the chat.
They asked that fluorescence emission spectra of the mixed metal oxides.
Yes,
actually,
metal oxides.
Actually, there is one called a solid fluorescence spectra. See, when you have the mixed one, first thing is you have to find out the fluorescence spectra of the each one. Suppose if you have titanium dioxide, and titanium dioxide is mixed with zinc oxide or some other oxide, samarium, tungstate and other things. Initially, you have to have that fluorescence spectra of that individual oxides. Then only you can analyze the fluorescence emission by using the mixed metal oxides. And normally, I mean, fluorescence spectra, that is called a solid state fluorescence spectra, because you cannot have it in the solution. So there is one available in the solid state fluorescence spectra. By that you can find out the emission spectra of the individual oxides, and also you can analyze the mixed metal oxides. Yes.
Thank you, sir.
I have another one question. Can I ask?
Yes, yes, please.
Okay, thank you so much. Thank you so much, Professor. It was very nice lecture. So my question is, I synthesize carbon nanomaterials. It's a highly fluorescent material. So my question is related to the fluorescence and Raman spectroscopy. So whenever I measure the Raman spectroscopy, due to the high fluorescence material of my carbon dots, I cannot predict and I did not get a very strong peak of the Raman. So why it's happen, and how can I prevent this, and how can I measure exact Raman spectra?
I have no, I mean, actually this, I have no idea about this Raman linking of Raman spectroscopy with the fluorescence spectroscopy, but there are something, I think you can refer the papers for that one, right? Because, I mean, this fluorescence spectroscopy is Raman spectroscopy, actually both are related to the only electronic spectrum. You can have it, but the thing is that the difference, I mean, the link between the Raman spectroscopy and fluorescence spectroscopy, it all depends upon what is that, I mean, circumstances in that. Unless we analyze and particularly know about that compound and other things, we cannot tell about this one. That is it. Or otherwise, you know, you can just send your questions in that, you know, chat box. I mean, I'll find it out and then give you an explanation in that, maybe in the mail, clear explanation in the mail. Okay.
Okay. Okay. Thank you, Professor. Thank you.
Hello.
Hello.
Hello. Good afternoon. Good afternoon. Can I say good afternoon because I'm from Malaysia?
It's not clear. I mean, that is. Hello.
Hello. Can you hear me?
Yes, yes.
Okay. So I'm Nuruddin Abdraman from University of Science, Malaysia, USM. A PhD student working with working on N-heterocyclic carbene salts and respective metal complexes silver.
Hello.
And are you hearing me?
No, audible in the sense not clear, but can you put it in the chat box? I mean that. Hello. Your question.
Okay. It's not clear.
Yes. Okay.
Hello.
Hello.
Okay.
Hello. It's not clear.
Your voice is coming, but your question is not clear.
Okay. So maybe I can.
No, just put it in the chat box now. What is that your question? So that I will see that.
Okay, I will put. Thank you very much.
No, now you can put it in the chat box. No problem. That I will wait and then.
Okay.
Hello. Hello.
Yes, sir.
Okay, maybe you stop the sharing, sir. You stop the sharing, sir.
Hello.
Hello.
Is he typing in the chat box? I mean that.
No, sir.
Okay, also, I mean, you can send to my mail also, with mail ID also, no problem.
Okay, yeah.
Okay, sir, definitely. So, thank you so much, sir. Now I invite Swati Burade ma'am to propose vote of thanks.
Hello, madam. One question is there.
Yes,
He has
sir.
written the question, okay?
Yes, 2
You can
minutes,
read
ma'am.
in short, yeah.
When I measured the Raman spectra of fluorescent material due to FL, Raman peak not observed. So how, why it occurred and how can I solve this issue?
See that Raman actually, we have not measured the Raman spectra of the fluorescent materials and analyzed it. So that's why I told that this one, and I can get that information and then from that, maybe from the papers and reply for this particular persons. Okay, because now we have not, I mean, worked on the Raman spectra so far till now. Okay, see this. That is why I am unable to answer for his question. So that I can find it out and then see how can we solve the problem. I can tell you about him. No problem. That. Hello.
Yes. Okay, sir.
Okay, right.
Yes. Please, Swati ma'am.
Swaminathan, sir, stop the sharing.
Hello.
Yeah, stop the sharing, sir.
Okay, okay. Yes.
Very good afternoon to all and happy National Science Day. I am Swati Burade on the behalf of Department of Chemistry, deem it a great honor and privilege to propose the vote of thanks on the today's session. Let me first of all start by giving glory of Almighty God for making this session successful. I owe my special thanks to Honorable Dr. Suhasini Vanzari, ma'am, President Amar Seva Mandal, Nagpur, Honorable Advocate Abhijit Vanzari, sir, MLC and Secretary Amar Seva Mandal, Nagpur, Dr. Smita Vanzari, ma'am, Treasurer of Amar Seva Mandal, Nagpur, for their continuous support and guidance. I also extend my special thanks to Dr. D.S. Badwai, sir, Principal Kamla Nehru Mahavidyalaya, Nagpur, for his valuable support and guidance. I express my special thanks to our today's guest, Professor M Swaminathan, sir, Visiting Professor, Nanomaterial Laboratory, International Research Center, Kalasalingam Academy of Research and Education, Krishnan Koi. Despite his busy schedule, gave time to grace this session and explained the fluorescence spectroscopy and its application. I also express my heartfelt thanks to Professor S.M. Gadegone ma'am, Head, Department of Chemistry, Kamla Nehru Mahavidyalaya, for her support and guidance, Professor W.P. Gurnule sir, for organizing such type of informative sessions, and Dr. M.S. Wagh, Kamla Nehru Mahavidyalaya, Nagpur, for her guidance. I also thanks all the faculty members for their valuable support. And lastly, I thank to all participants. Thank you all. Thank you so much, sir.
Rashmi madam, we are taking one photograph, okay?
Yes, sir.
So participants are requested to switch on your video camera. Vajpayee madam, thank you for joining. Okay. It's okay now. Thank you. Swaminathan sir.
Hello.
Thank you, sir.
ओके सर, स्वामीनाथन सर को भी नमस्ते सर।
Thank you, sir. And happy National Science Day to all.
Thank you, madam. Swaminathan sir, now we are ending the meeting. Okay,
Okay, thank you.
Okay, sir. Thank you for nice lecture.
Thank you very much, sir. Thank you for your patient hearing and all these things. Thank you very much. Okay, I'll leave, huh?
Yes, sir. Yes.
Yes, sir.